Usually when we talk about a medical diagnosis, there's this expectation of, well, precision, right?
Yes, absolutely. It's like engineering.
Exactly. You break your arm, the x-ray shows that jagged white line, and the doctor just points and says, there it is.
Yeah, the signal is obvious.
Right.
That-
But then you step into the world of multivariate time series forecasting, and suddenly it feels like that x-ray machine is, it's fundamentally broken.
Good way to put it.
We are looking at a diagnostic landscape that is entirely murky. And for those of you listening today, the quants, the machine learning engineers, the data scientists, you know exactly what I'm talking about.
Oh, they definitely do.
Time series data is notoriously, almost aggressively sensitive to noise. And your current options for automated feature engineering are essentially split into two really flawed camps.
Yep, the classic dilemma.
You are either relying on handcrafted, domain-specific heuristics that take weeks to build and honestly fail to generalize, or you're throwing raw data into opaque end-to-end representation learning models.
And those models, they end up wasting massive amounts of their parameter capacity just trying to model pure noise.
Right.
It is the absolute definition of diagnostic muddy waters. And that wasted capacity you mentioned is a critical bottleneck in modern deep learning architectures.
It's just a huge drain on resources.
Exactly. When a complex model has to simultaneously clean the data, figure out the cross-sectional correlations, and map the autoregressive dependencies, its predictive accuracy inevitably suffers.
Because it's doing too much at once.
Right. The model is so busy trying to figure out what the signal actually is, it fails to forecast where the signal is going.
Well, what if I told you there is a way to fix that x-ray machine?
I'd say I'm listening.
A way to mathematically guarantee you are extracting the right signals using the fundamental laws of statistical mechanics. So today, we are doing a deep dive into a framework that attempts to do exactly that.
It's a fascinating piece of work.
The paper is called Feature Programming for Multivariate Time Series Prediction. And our mission today is to unpack what is arguably the first theoretically grounded automated feature engineering framework.
Which is a bold claim, but they back it up.
They really do. If traditional feature engineering is like artisanal trial and error crafting, where you just throw moving averages at the wall to see what sticks to it, the framework in this paper is a physics-based programmable factory.
I love that analogy.
But to understand how this factory mathematically guarantees it is capturing the necessary signals, we first have to understand the rather radical physics model it is built upon.
Right, the underlying engine.
Yeah, the authors call it spin-gas-Glauber dynamics. And it really requires us to look at time series data in a completely different way.
The shift in perspective here is foundational. Instead of looking at a time series macroscopically, say, an hourly temperature reading or a daily stock price, the authors zoom all the way in.
Down to the smallest possible time scale.
Exactly. They propose treating a multivariate time series as a path sum of infinitesimal increments.
Okay, so breaking it down to the absolute microscopic level.
Right. If you imagine two data points separated by a specific time interval, the transition from point A to point B isn't modeled as one big jump.
Makes sense.
Instead, it is the cumulative sum of a series of Markovian coin tosses happening at a microscopic level.
Wait, whenever we start talking about microscopic binary outcomes, these coin tosses, it immediately brings to mind the Ising model from statistical mechanics.
Yep, the classic Ising model.
But the classic Ising model is static, right? It's used to model ferromagnetism, where you have a lattice of spins pointing either up or down.
That's right.
But since we are dealing with time series forecasting, we obviously need dynamics. Things change over time.
And that brings us to Glauber dynamics, which you can basically think of as the dynamical version of the Ising model.
Right, so adding the element of time.
Exactly. So in standard Glauber dynamics, you assign new values to all the spins at the next time step probabilistically. And, this probability is based on what they call an effective local field.
An effective local field. Okay, what does that actually mean in this context?
It basically summarizes the structural contributions from all the other spins in the network. It measures how much a particular spin's neighbors are trying to align it with themselves.
Okay, to put that in perspective for you listening, standard Glauber dynamics is a bit like a political poll.
Well, that's a good way to look at it.
A voter, which is our spin in this case, looks at their neighbor's current choices before deciding which way to lean.
Right.
But the authors modify this classical concept into what they call a spin gas model. If the standard model is just looking at current choices, what does the spin gas modification actually add to the equation?
Well, it adds the elements of motion.
Motion.
Yeah. The authors redefine that effective local field mathematically. Let's denote it as gamma.
Okay, gamma.
In their modified model, gamma still contains the traditional structural interaction matrix, the neighbor's current states. But it has a novel gas-like interaction term.
And what's inside that gas-like term?
Specifically, they introduce discrete counterparts of momentum and acceleration.
Oh.
Yeah. They define momentum as the first derivative of the spin state with respect to time, and acceleration as the second derivative.
So they're bringing high school physics into the microscopic network.
Exactly. By injecting this into the local field, the probability of a spin flipping at the next microscopic time step depends not just on the network structure, but on the trajectory and velocity of the system states.
Okay, keeping with the pole analogy, your neighbors aren't just influencing you based on their current opinion. They're influencing you based on how fast they're changing their minds.
Yes.
And whether that rate of change is actually compounding over time.
That is the perfect way to visualize it.
Okay, but that makes intuitive sense for microscopic binary states. Here is the friction point, though.
Sure, lay it on me.
A time series in quantitative finance or like traffic forecasting, it is not a sequence of microscopic binary coin tosses.
No, it's not.
It is continuous macro-level data flowing over time. So how does the paper mathematically bridge the gap between this discrete spin gas model and the continuous data you and our listeners actually work with?
Right, that's the big leap. They achieve that through a really rigorous coarse graining process, moving it to the continuous time limit.
Coarse graining, like zooming out.
Yeah, I think the best way to visualize this is to imagine looking at a pointillist painting.
Okay, like a Georges Seurat painting.
Exactly. Up close, all you see are thousands of tiny discrete dots. Those are our Markovian coin tosses.
Right.
But as you step back, which represents mathematically taking the continuous time limit, letting the time intervals approach zero and the number of steps approach infinity, those individual dots blend together.
If they form an image or a smooth line.
Right, they form a smooth, continuous line. And that continuous line is represented mathematically as a path integral.
Okay, so they are borrowing the path integral formulation, similar to what we see in quantum physics for diffusion processes.
Yes, the methodology is very similar. When you write out the conditional probability of the system moving from one state to another over a given time interval, it becomes proportional to an integral over all possible paths.
And that integral is weighted, right?
Yeah, it's weighted by the exponential of an action functional. The action functional is essentially the integral of the system's Lagrangian over time.
Let me stop you there. Because we defined our microscopic spin gas model to include momentum and acceleration, does that directly infect the continuous model?
It infects it. It dictates it entirely.
Oh, really?
Because the original discrete dynamics explicitly incorporated momentum and acceleration into the local field, the resulting Lagrangian in the continuous limit inherently relies on those derivative components.
So you can't escape them?
You can't.
Hmm.
Taking that a step further, this provides a profound foundational justification for feature extraction in data science. Well, the path integral formulation mathematically proves that if you want to model the most probable path a time series will take, you cannot simply look at the raw position data.
You need the whole picture.
Right. You must account for both the denoise conditional mean and the fluctuations, specifically the momentum and the acceleration.
So it fundamentally takes derivative-based features out of the realm of, like, empirical rules of thumb and actually grounds them in the laws of physics.
Exactly. It's a huge shift in how we justify our features.
So if this physics-based framework theoretically builds the perfect mathematical mirror of a time series, the obvious question is how we actually use it.
Right. Theory is nice, but we need application.
Because real-world machine learning doesn't run on abstract Lagrangians on a whiteboard, it runs on software pipelines.
Very true.
And the authors claim to operationalize this into something called feature programming. How exactly do they translate that continuous time physics intuition into a scalable pipeline that a data scientist can actually deploy?
So they structure it as a three-step pipeline. The first component is a customizable feature template.
Okay.
The second is a programmable operation module. And the third is the automated hierarchical generation.
Let's focus on this second one for a second, the operation module.
Yeah, that's the core engine here. It's where the authors distill their physics model into three highly abstract operators: difference, window, and shift.
Let's break those down. What is the difference operator actually doing under the hood? I assume it's not just a simple subtraction of today's value from yesterday's value.
Oh, far from it. The difference operator is a generalized derivative operation.
Okay, so it's more sophisticated.
Yeah, it smoothly combines subtraction with local smoothing. It is specifically designed to extract curvature-like features.
Curvature-like features, so the momentum and acceleration again.
Exactly. The exact momentum and acceleration components dictated by the Lagrangian we were just discussing.
Got it. And what about the window operator?
Then you have the window operator, which is motivated by the need to capture denoised summary statistics from multiple resolutions.
Like looking at different timescales.
Right. It extracts the maximum, minimum, and mean over various lookback sizes, which handles the time rescaling property of the input series.
Okay, and the last one was shift.
Finally, the shift operator allows the framework to incorporate auto-correlated information by creating new series with arbitrary time differences.
Okay, I have to push back here, or at least play devil's advocate for our listeners.
Go for it.
Calculating differences and running rolling windows over various look-back periods is not exactly a groundbreaking concept.
No, it's pretty standard.
Any practitioner using Python and Pandas does this daily. What makes this framework fundamentally distinct from an engineer just writing a script to generate rolling means and diffs?
It's a fair question. The distinction lies entirely in the architecture, specifically the programmable order-by-order upgrade architecture.
Order-by-order upgrade, what does that mean?
Well, when a practitioner writes a Panda script, they're typically generating a flat, static array of heuristic statistics. They're just guessing at what might be useful.
Right, throwing things at the wall.
Exactly. This framework, however, is a systematic hierarchical flow guided by an order upgrade rule. The features are categorized mathematically.
How are they categorized?
The raw data is considered your zero-order position.
Okay, step 0.
When the system applies the difference operator to that zero-order data, it mathematically upgrades it to first-order momentum.
Oh, I see.
And when it applies the operator again to the first-order data, you get second-order acceleration. The system automates this hierarchical generation, carefully flowing features from one level to the next based on the physics we outlined earlier.
But what if I don't want to rely solely on the basic physics features?
What do you mean?
In quantitative finance, for example, a fund might have a highly proprietary formula for absolute energy, or a domain-specific calculation for momentum that they know works for their specific asset class. Can this factory accept that kind of inductive bias?
Oh, it is explicitly designed to.
Really? It doesn't break the system?
No, the feature template is not a closed box. At each order 0, first, and second, the user can seamlessly inject discretionary domain-specific features.
So I can just drop my formula in?
Exactly. If you drop your custom absolute energy formula into the template, the framework doesn't just calculate it in isolation.
What does it do?
It assimilates your custom feature into the order-by-order flow, upgrading it and mathematically combining it with the physics-based basic features. It's a structured pipeline that accepts custom inductive bias without breaking the underlying theoretical flow.
Wow, okay. Since you mentioned the theoretical flow, we need to examine the mathematical proofs in this paper.
Let's do it.
The authors make a very bold claim that this is the first theoretically grounded automated feature generation method, and they lean heavily on Theorem 5.1 in the paper.
Yes, Theorem 5.1 is the anchor.
Walk us through how they actually prove that these generated features represent the true underlying system, rather than just being a highly organized set of heuristics.
So to prove this, the authors analyzed the joint distribution of the coin toss process we talked about earlier.
The microscopic Markovian ones.
Exactly. They analyzed the path probability between consecutive time steps, and they model this path as an undirected temporal joint graph.
Okay, an undirected graph.
Imagine a graph made of two subgraphs, one representing the system at time t and the other representing the system at time t plus delta t.
Okay, so they have this graph of probabilities mapping the transition. But how do you mathematically prove that extracting momentum and acceleration from this graph captures the whole picture?
They borrow a brilliant mathematical technique from a 2015 paper by Yang et al.
What did that paper establish?
That framework establishes a method for constructing multivariate graphical models strictly from univariate exponential family distributions.
The exponential family. Let's remind the listener what that is.
Think of the exponential family as the well-behaved class of probability distributions in statistics. Things like Gaussian, Poisson, or binomial distributions.
Right, the ones with nice properties.
Exactly. They have incredibly useful mathematical properties, particularly regarding sufficient statistics. And the authors prove in Theorem 5.1 that the node conditionals in their temporal joint graph actually follow a univariate exponential family.
And those node conditionals are governed by that modified spin-gas-Glauber dynamics we talked about earlier.
You got it.
Okay, so if the node conditionals fit perfectly into this univariate exponential family, what does that actually allow us to do mathematically?
It allows us to lock down the entire multivariate network.
Just from the univariate pieces.
Yes. Under the conditions identified specifically when the gas-like interaction term takes a tensor factorized form involving up to second-order time derivatives. Those simple univariate node conditionals uniquely determine the entire multivariate joint distribution.
Wow.
Uniquely determine it up to pairwise sufficient statistics. And the crucial breakthrough of Theorem 5.1 is that these sufficient statistics are mathematically extended to include the first and second order time derivatives.
Okay, so to make sure I am fully grasping the weight of this, by proving that momentum and acceleration act as these extended sufficient statistics, what is the ultimate consequence? Are we saying we can perfectly reconstruct the system?
We are saying exactly that.
That's incredible.
The theorem guarantees that the ground truth random process governing the time series is uniquely represented by these derivative extended sufficient statistics.
So it's not just a good guess anymore.
Right. This is the ultimate so what of the paper's theoretical section. It ensures the feature engineering process isn't just an empirical guessing game.
You actually have the math.
When your features perfectly map the sufficient statistics of the exponential family governing the data generation process, you have built a complete mathematical representation of the system's state.
Which means you capture everything.
Everything you need to know about the system's trajectory, which enables highly efficient inference downstream.
That theoretical elegance is fascinating. But for our listeners who actually deploy these models in production environments, math on a whiteboard doesn't always translate to performance on a server.
No, it rarely does without a fight.
Real-world data doesn't care about beautiful proofs. It is noisy, it has missing values, and it's highly unpredictable.
Absolutely.
So let's look at how this framework performed during empirical validation. The authors tested this across several datasets, including synthetic data, traffic, electricity, and notably, the taxi dataset.
The taxi dataset is the perfect stress test to highlight here.
Why is that one so tough?
The authors specifically note that it is the noisiest dataset of the group. It has a temporal signal-to-noise ratio of just 1.27.
Wait, 1.27?
Yeah. When your signal is barely louder than your noise, forecasting becomes an incredibly difficult environment for any architecture.
And they threw a massive variety of architectures at this problem to see if the features generalized, right?
Oh, they threw everything at it.
They tested standard multi-layer perceptrons, CNNs, LSTMs, gradient boosting models like XGBoost and LightGBM, alongside transformers, temporal convolutional networks, and state-of-the-art models like TFT and NBeats.
It was a very thorough gauntlet.
And the results were universally positive. Just by injecting these extended physics-based features into the pipeline, the taxi dataset's R-squared score jumped by roughly 4 to 6% across the board.
Which is huge for data that noisy. But, the most revealing result came from the multi-horizon prediction task on the synthetic dataset.
What was the setup for that one?
They tasked these models with predicting the next 20 values into the future, using a historical sequence length of only 20.
Oh, so a 1-to-1 ratio of history to prediction. That's tough.
Very tough. When the models were forced to rely solely on raw, basic features, they struggled significantly. However, when they were fed the extended features generated by the feature programming framework, the performance leap was staggering.
What kind of leap are we talking about?
The model showed an average 88% improvement in R-squared.
Wait, an 88% improvement? That's insane.
Yeah, and an over 27% improvement in Pearson correlation.
That's a massive jump. Looking at the tables in the paper, there is an observation that really stands out to me regarding the different architectures.
Which one?
It is fascinating that feeding these extended features into a relatively simple standard transformer allows it to achieve performance that matches or even beats highly complex specialized architectures like the temporal fusion transformer or NBeats.
Assuming those complex models are only given the raw features.
Right. It's like giving a basic algorithmic model a pair of X-ray glasses. It suddenly sees the underlying structure without needing the complex architecture to deduce it.
That observation strikes right at the core of the representation learning problem we discussed at the very beginning.
How so?
Well, why do researchers build massive, highly complex architectures like NBeats? They do it because they were trying to force the neural network to learn the representations, the physics, the momentum, the structural correlations from scratch.
Ah, so the model has to figure out the rules of the universe first.
Exactly. The model has to iteratively deduce the laws of physics through stochastic gradient descent.
Mhm.
But because the extended features generated by this framework so perfectly capture the autoregressive and cross-sectional information via those guaranteed sufficient statistics, the predictive model itself is relieved of the entire burden of representation learning.
It doesn't have to learn the physics anymore.
No, the mathematical features do the heavy lifting. The neural network just has to learn the final mapping from the features to the target, which is a vastly simpler and more stable optimization problem.
And we cannot ignore the computational efficiency of doing that heavy lifting up front with mathematics rather than backpropagation.
Oh, the speed is incredible.
The paper notes that the hierarchical feature generation process takes mere seconds to execute. If you compare that to the hours or sometimes days required to train a massive downstream architecture to empirically learn those exact same representations, the savings in compute are massive.
Which is highly relevant for practitioners operating in today's resource-constrained environments.
You're saving so much time and money.
You are effectively trading a highly opaque, computationally expensive stochastic optimization process for a transparent, mathematically guaranteed, deterministic feature generation pipeline that executes in seconds.
It's a win-win.
It allows you to use simpler, faster models while achieving state-of-the-art accuracy.
We have covered a tremendous amount of complex ground today, so let's synthesize the main takeaways for you, the listener. We started with the universal frustration of modeling highly noisy multivariate time series, where models waste their capacity trying to learn pure noise.
And we explored how the authors shifted the perspective entirely, zooming into the microscopic scale with spin-gas-Glauber dynamics.
Right. By modifying the local field to include momentum and acceleration, and then applying a coarse graining process to reach the continuous time limit, they derived a path integral representation that proves derivative-based features are a fundamental requirement of the system's physics.
We then saw how that theoretical physics intuition translated into a highly systematic feature programming software pipeline.
Using the difference, window, and shift operators.
Exactly. And guiding them with an order upgrade rule. The framework automates a hierarchy of features while still allowing for domain-specific inductive biases.
And crucially, this isn't just an empirical pipeline. Theorem 5.1 proves via univariate exponential family theory that these extended features act as sufficient statistics, uniquely and perfectly mapping the state of the ground truth process.
Which ultimately leads to massive, universal performance boosts across both simple and complex ML architectures.
Allowing a standard transformer to rival state-of-the-art deep learning models on incredibly noisy real-world data. We moved from trial-and-error artisanal feature crafting to a mathematically guaranteed, programmable factory.
It represents a paradigm shift for the field. I mean, it moves us away from the mindset of let the deep learning model figure out the features empirically and brings us back to let the mathematics perfectly define the features deterministically.
And I want to leave you with a final forward-looking thought to mull over based on that paradigm shift. If this framework can theoretically build a perfect mathematical mirror of a time series by utilizing position, momentum, and acceleration as sufficient statistics, could we eventually invert this process?
Oh, that's an interesting idea.
In the future, could we use these programmable derivative-based features not just to predict the next data point in a sequence, but to systematically reverse engineer and discover the hidden differential equations that actually govern completely unknown black box systems?
That would change everything.
It's a fascinating possibility for the future of scientific discovery. Until next time, keep diving deep.